Yeah, hello everybody. I'm Andreas. My talk for today is about virtualization. Perhaps a few words about me. I'm a computer science student from Aachen, and I like everything which every stuff that is close to the hardware and bare metal, and I like embedded devices and operating system development and all that kind of stuff. So that's one of the reasons why I did this virtualization stuff I'm presenting today. The outline of this talk is I have a very short introduction about the whole topic, why I did this simulating thing, what I'm going to show in this talk. Then the main part of this talk is how several virtualization techniques we use today work, and what they are supposed to do, what are their advantages and disadvantages. Then I'm going to present the VM32. It's my simulator for learning purposes I wrote. Then I'm going to show very briefly how you can implement a hypervisor with with not even much code on this platform. And yeah, I've got one slide of a conclusion. That's all. So yeah, the introduction. What this talk is about. It's in part my bachelor thesis I wrote over the last half year, and where I implemented the simulator. The simulator is actually designed and written for learning purposes, so it's not really for daily usage or something. It's just to demonstrate how all these concepts work, and to give students or people who are willing to learn a tool where the people can just write some assembly and without completely writing an operating system or bootstrapping a complete modern chip, which takes a while because they have just too much features. And there are several things you can virtualize. You can virtualize networks, storage, and so on. And what I'm going to talk about is we are just virtualizing CPUs. CPUs and memory, essentially. So the RAM, the main memory of a computer. But there are some concepts for virtual memory management in virtualization techniques which are quite complex, and unfortunately I won't have enough time for that. It's a bit complex. There are several techniques. If you're interested, please come to me after the talk and I'm going to explain it to you. And yeah, as I said, the simulator, and please see it as an introduction to a very complex and wide topic. And it's like TCP/IP for beginners, but with virtualization. Yeah, one slide, obligatory history lesson. IBM started researching and developing virtualization techniques in the late 60s. I think it was 1966 or something. That's at least the oldest paper I found they published. It's somewhere in ACM or IEEE Explorer if you have access to those papers. Then you can look that up for yourself. I think it's called A Survey on Virtual Machine Virtualization or something like that. Yeah, they started implementing a virtual machine monitor on their big mainframes with many users on there, and the reasons they had in the past are basically exactly the same as today. And I'm a techie, so there is not much marketing stuff on this slide. Just very briefly, what virtualization can be used. So I think most of you already know that. It's very handy for testing new software. You don't have to crash your working machine to test some software. You can run outdated software which maybe is not even supported on modern operating systems. You can just install an older operating system and for migrational purposes or something like that. Then a very strong point is developing new drivers or operating systems, because having a second real box next to your desk and keeping it constantly crashing is kind of a pain if you develop on real hardware. And yeah, consolidating servers. you have 20 machines idling and consuming power, which is not good for the environment and also for your budget. So you just take those 20 machines, the services on these machines, the operating systems on these machines, put it in one box, and you only have one box which is, well, moderately, has a moderate CPU usage afterwards or something like that. Then you can, of course, host vulnerable stuff in a hypervisor and start praying that no one is able to escape this hypervisor, because that's perfectly possible. It's basically just another layer. It's not really a security feature. It's just another barrier an attacker has to overcome to own you completely. And once he's outside of the hypervisor, you're screwed. Then you have the possibility to instantly spin up new instances of your software. This is what we call the cloud. And you can do failover migration, for example, for redundancy reasons. And there are many, many more reasons, but these few. So, in general, what is virtualization? What do we want to achieve on a technical level? What we want to introduce an abstraction between the operating system and the real hardware. And if we control this abstraction layer, we can basically make the guest operating system or the guest software running on this virtual platform we are emulating, virtualizing, whatever. Then we can make the software see what we want it to see. Especially if you need special environments for testing. Did you ever ask yourself how you test a scheduler with 256 CPUs or memory management in an operating system kernel with 1 terabyte of RAM or something like that? You can, of course, tell the guest software, you have 256 cores, even if you don't have them in the real machine. You just have to emulate them and make the machine behave some kind of the real machine. Of course, you're not going to get the performance out of 256 real cores with, for example, a quad-core machine, but you can at least try to simulate the behavior of having 256 cores, a terabyte of RAM, and so on. And we can also introduce quotas. For example, if we have real words, live software running somewhere, on a shared environment where several users are running stuff, then we may want to introduce quotas on network usage, on CPU usage, on storage, and so on, which we can do because all the hardware usage is going through this abstraction layer. And for that we can redirect hardware accesses. We can have complete virtual networks on one machine with virtual network interface cards and virtual storage and so on. So so much for the introduction. Now virtualization itself. I've got this image basically shows you an operating system, what it looks like in some kind of block diagram. On the bottom, you obviously have the hardware, and the top two boxes, the two boxes in the top are so-called privilege levels. They are software domains where software is running in. We have normally two modes for an operating system, for a modern operating system. It's a kernel mode and the user mode. And in the kernel mode, the kernel runs. The kernel is the core of the operating system, and this core is able to communicate directly with the hardware. It can configure your network interface card, it can configure your SATA controller, and so on. It can switch CPU states, CPU modes, so it has direct access to the hardware. And of course, it does configuration of the hardware via so-called privileged actions. Those actions are very, very specific to the platform you're running on, so that's normally where you consult the platform manual or the CPU reference manual. And then on the top, you have the user mode, and every process that runs on a machine has to use the so-called syscall interface, which the kernel offers to user mode programs. And this syscall interface is different for every operating system, but on Linux, for example, it's stable, it's always the same. If you adhere to the specification, then you can use that in every Linux kernel. An example for a syscall is open a file, write to a file, read from a file, and so on. So the basic services the kernel offers, like the file system scheduling, the memory management, and so on, are completely handled by the syscall interface. Of course, the kernel checks if there are several limits. If the user mode processes violate some limits, like read file protection, if the process the process runs with is even privileged to access a file or something like that. So yeah, the privileged access I already explained that. So what if we introduce two kernels, because we want to run two kernels, basically, because we have several operating systems we want to have on one machine. So there is no way that this could ever work, because those two kernels are going to interfere with each other because they don't know that there are two kernels. So they both would try to access the hardware and would configure the hardware differently, which is not going to work. Also, we cannot abstract the hardware. We don't have this abstraction layer, so we don't have control over what those two or more kernels actually do to the hardware. So we need a different approach. This is just one example. There are several architectural differences, different approaches to this, but this is, for example, one hypervisor or virtual machine monitor. I'm using this this word. Yeah, it's basically the same. So on this slide, you see a hypervisor with a virtual machine monitor running in kernel mode, and this virtual machine monitor essentially replaces a kernel, an operating system kernel. And now every kernel has to use some other interface, either dedicated interface, what we will see that later on the concept slides, or a hardware feature. The virtual machine monitor in kernel mode is used then to abstract the hardware and redirect disk accesses, network interface, cards, and so on. So yeah, all the boxes in the top are guest instances of software running on your virtual machine each. So yeah, there are 4 solutions for this two-kernel problem. It's hardware-assisted virtualization with hardware features. It's para-virtualization, which is completely software-based. There is binary translation and emulation, which are also completely software-based. The hardware-assisted virtualization introduces a new CPU feature. Every modern CPU nowadays has this feature. Intel, it's called Intel VT. On AMD, it's called AMD V, I think. And those features introduce the possibility to persist a complete execution context of running code, put it somewhere in memory, and restore another context. And there is generally one hypervisor context where the whole hypervisor lives and does its stuff and manages all the guest contexts, and several guest contexts. Of course, for each guest, you run one context. And you can switch between those contexts. And yeah, there are several events during the runtime of a computer where one of those context switches happen. The first one is it is explicitly requested by code. So the hypervisor says, please, CPU, load this state of this machine and jump and resume execution to enter a VM. This is, most of the time, it's called a VM enter event. Then there is a privileged action performed by the guest, like accessing memory, which is not present, configuring the CPU for a different mode, and all kinds of stuff. And this is where automatically a transition back from the guest mode to the hypervisor mode occurs. And then the hypervisor can handle this access or kill the machine or whatever. Or a hardware interrupt or an exception occurs. That means some attached device to the computer pulls on an interrupt line on the CPU, and the CPU has to react to get data from the hard disk or the network interface. And then the guest mode is also persisted and the hypervisor mode is loaded again, so that the hypervisor can handle the real hardware events. And upon a change back from the hypervisor to from the guest to the hypervisor mode, the hypervisor gets extra information what happened. Yeah, and normally it returns back into the guest it came from, another guest, or it kills the guest. So with this mechanism, you can also implement scheduling between different VMs and choose the next VM with different rules, which is going to be executed. So the advantage of this approach is that the guest operating systems don't need to be modified, obviously, because you can just run them in this other context, and they don't even, the code has the ability to detect that it's running virtualized, but that's, well, you don't need to modify the code to run. You can use stock Windows, install it in a VM, and it works. But explicit hardware support is necessary as a disadvantage. Then there is the para-virtualization. The para-virtualization is another approach. It's the kernel of the guest is completely modified. Every privileged access is stripped from this kernel. And the hypervisor, which runs in kernel mode, offers, much like the syscall interface, a hypercall interface. So if you don't have any privileged actions in your code, you can just run the kernel in user mode in user mode. And every time it needs to perform some privileged action, it asks the hypervisor to do that for it. And most of the time, a hybrid system is implemented together with the hardware-assisted virtualization and the para-virtualization, because the CPU is then hardware virtualized, and all the I/O devices, HDD, network interface, graphics card, are para-virtualized. So the kernel just loads different drivers which know basically that they are virtualized, and they just use another interface. Instead of talking directly to hardware via memory-mapped I/O registers, they are just asking the hypervisor to display an image to the screen or read a sector from the hard disk. Because this is done for performance reasons, because it's much, much faster than emulating real hardware, because obviously real hardware is not made to be emulated by software, so this gets slow, and you can just use the faster interface if it's offered anyway, just by loading drivers. So the advantages here are that the hypervisor is more simple in most cases, because most of the functionality for that is often already implemented in an operating system, like memory, like mapping memory, talking to I/O devices, and all that kind of stuff is already there for user mode processes. So you can reuse much of the code. It's relatively fast because it's every guest you virtualize is just a user mode process, like a regular process on an operating system. But the guest operating systems need to be heavily modified, of course, which is only possible with open source operating systems. There is a Windows 7, Windows XP version modified by Microsoft Research to be run under Xen with para-virtualization, but it was never made public because of licensing issues, obviously. Yeah. Oh, I forgot one thing. The hardware virtualization is mostly used by today. It's used by every modern virtualization software. That is VMware, Xen, Parallels. The para-virtualization is implemented by Xen, and I don't know if there is any other software. But Xen also does real hardware-assisted virtualization. Then there is another approach, the binary translation, which is a bit more complex. What happens there is it's also a complete software solution. The code to be executed in a VM is split in so-called basic blocks. Each of those blocks can have more than one entry point. We'll see that on the next slide. This is code split into basic blocks. Each of these basic blocks has one entry point, several entry points, can have several entry points, and exactly one exit point. No, that's not true. Yeah, it has more than one entry point and one exit point, of course, except there is a branch, a conditional branch. So there are, here you can see 4 blocks where code is in. So this is a Hello World program. It just looks at the first argument. It's x86 Intel assembler. It just looks at the first argument. If the argument is set, then it prints hello, the argument. Otherwise, it just prints hello world. And this is the branch. You can see the red and the green arrow, because it checks if actually the length of the arguments is 2, and if it is not 2, it jumps into hello world. If it is 2, it jumps into hello in the hello %s branch. So the binary translator takes each of these blocks, or one of this block at a time. Like, let's begin with this first one on the top. And it translates, it looks at the code and it translates it from a source platform to another destination platform. It can be the same, but it doesn't have to be the same. And all the privileged instructions are just replaced with callbacks, basic function calls back into the binary translator where it is then handled and the behavior is emulated. The block, after it's being translated, is put into memory, and then it's executed by the CPU. At the end of the block, like this jump if not 0 instruction in the top block, the CPU jumps back into this loop, and the next block to be executed is determined, and then it's also again translated. It's the privileged actions are replaced with callbacks, and the cycle repeats. Of course, there's some performance for performance reason. There is caching and so on happening, but yeah, that's the basic algorithm that happens there. So the advantages here again: the guest operating systems don't need to be modified because they are just translated on the fly, and you can execute code for different architectures. You can run ARM code on x86 hardware because it's just being translated from ARM to x86. And the approach can be used to dynamically instrument running code. There is a tool from Intel called Pin Tools, and you can look live at the binary and write programs which look at certain points and do which do stuff and dump some information also. This is also done by binary translating it and injecting calls back to your own code so that it gets ran when the time has come for the instrumenting code. But the binary translator can get very complex very fast, especially if you want it to be fast. Then the last thing you can use for virtualization is the classic emulation. The code, this is the easiest one. The code is emulated instruction by instruction. So there's a program. It looks at the current instruction pointer of the virtual emulated CPU. It determines what it does. It does it. It persists it somewhere in a state. Like you have somewhere in memory, you have registers of the virtual CPU. You write back this result of whatever instruction you're currently looking at in whatever you are currently executing back into this state, and you do that with the next instruction and so on. And it's essentially a CPU implemented in software. It's mostly used for old platforms because it's very, very slow. The C64, the Nintendo Entertainment System, the Super Nintendo Entertainment System, Game Boy, and so on, and so on, and so on. Also, the guest operating systems, if there is one, I mean, the Game Boy doesn't really have an operating system, doesn't need to be modified. It can be made cycle accurate. This is the only emulation is the only thing that can be made cycle accurate. You can, in fact, add sleeps if your CPU is reasonable fast. You can just add sleeps, and you can exactly emulate. It is not very easy, but it is possible. Each instruction with taking exactly the duration the original platform would also need for performing this instruction. So this is very important for gaming, of course, for old platforms. Yeah, and the emulator is less complex than a complete binary translator because it's just a big switch case or if. But it's very, very slow. So it's mostly used for old platforms which are slow anyway. So much for basic principles. The VMs of virtualization. The VM32, I wrote some sample code for hardware-assisted virtualization. It's not really virtualization, but this is coming. I'm going to explain that in the conclusion. But I hope that the concepts are clear. So the features of this CPU I designed and developed, which was not very easy, are an orthogonal instruction set. You have 31 registers. You can access memory with register indexes, so you can say, look at address OX1000 and add the contents of register 1 to that address and fetch some value from there. It has a hardware stack, so you can, much like x86, push and pop values. You have segmentation for memory protection. You don't have real virtual memory, but you have segmentation, how that works and what it is. There is a slide later. And it has hardware virtualization features, a hardware timer for doing timer-based interrupts. And I emulate one single hardware access by a special print instruction, which does nothing else than just taking the value you want to print and dump it to standard out. And you have, of course, control registers for controlling the segmentation, the virtualization, this, and so on. The timer, the interrupt behavior. And so the complete toolchain I wrote in Python consists of an assembler, a linker, a debugger, a simulator, and a disassembler. So you can really work with that stuff because I needed all those tools to develop it initially. And this is what a basic Hello World looks like. It's just the beginning. There are 2 more slides. If you're not familiar with assembler, this is how it looks like. You have all the instructions that start with a dot are control sequences for the assembler to tell it how to behave. And yeah, it tells basically the linker afterwards that all this stuff is put into a segment called vectors. It's has nothing really to do with the segmentation itself, but it's just a point in memory where this stuff is put at later if the binary image is constructed by the linker. So what we do here as a first instruction is this move. The R30 is the stack pointer for the hardware stack. So we just put the address where the stack ends there because the stack grows downwards, and then we in the next instruction we push a pointer to a string on the stack, and then we call sub-function called print string, which obviously calls it's named print string because it prints a string. And then after that, we just halt the machine, and in case it does somehow another thing, it just jumps again back into the halt instruction, which is kind of unnecessary because the simulator terminates upon seeing a halt instruction. This is the print string function. It looks a bit strange. There is this weird enter and get argument instruction. Why I need that? It's the reason for that is the segmentation. It's a bit too strict because I can't access the stack, which is a design fail. But that's a point in the conclusion. The first argument is fetched into register R0. Then there is a loop, starting at the next char label. The current character the R0 points at is compared with 0. 0 indicates the end of a string. If this result is 0, then the CPU jumps to the end label with this jump if 0 instruction, JZ. Otherwise, it just executes the next instruction, which in this case is the print instruction, which just prints this current value at the pointer. It adds 1 to the pointer, so it advances the pointer in the address of the pointer to the next character, and then the cycle repeats, and yeah, it prints characters until it hits a 0 byte. And after we are done, we're calling this leave and this red N1, which removes the pushed, the red N1 removes the pushed argument, the pointer to the string. And this is how the string looks like. There are two more segments. There is the data segment and the stack segment where data and the stack lives. And we have this label string greeting, which is just the hello world string. So I already I have that as a demo. So is that big enough? I think so. Yeah, you have several scripts here: the linker, the simulator, and so on. So to execute the simulator, the code will be public after the presentation on GitHub. If you want to play, if you want to extend it, whatever, please do so. Simulate the Pi examples, print string, right? Test.bin. Yeah, and it prints hello world 2 times because the code is a bit different. I'm printing 2 strings here, but it executes the code and it prints hello world. So another hardware feature I implemented, the segmentation. It's memory protection. So if you want to have guest operating systems running later, then you don't want one operating system to look in the memory or write into the memory of another operating system or even the hypervisor, because you could get a privilege escalation by that. If I can if I as a guest can configure the hypervisor, then yeah, I can tell it what to do. We don't want that. And segmentation is another concept compared to virtual memory. It's entirely different. It's much older, and it's just windows pointing into memory. It has a start address and a limit address, and or size. And if the CPU tries to execute code, fetch data, or do operations on the stack outside of this window, then the rules are violated, and an exception is thrown so that the hypervisor can react on that. And I have a segment for code, for data, for stack, and for registers, because registers are actually not really registers, but they are aliased into memory. Why that is later. And you can activate those segments by just selecting a segment with several control registers: CS, DS, ES, RS, and SS for the code segment, the data segment, the extra segment, the register segment, and the stack segment. If you're familiar with the 8086, then you know already these registers, because they're named the same. There is just no register segment. Yeah. All this is managed by a table. This table looks like this. It's also, again, in assembler syntax, so you can just format that nicely in a text editor. And we have here the segmentation table for the hypervisor and a first VM. And it's just a table where 2 addresses are in each row. The first one is the start address, where the segment starts. The limit field is the end address. Then there is a type. 0 stands for code, 1 stands for data, 2 for registers, and 3 for stack. And there is an unused privilege level. This privilege level should do something, but it doesn't yet, because there's a good concept missing how to implement that. And to tell the CPU that the table ended here and it can stop loading the table from memory once you load it, there is just 4 of those OX, F, 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 F words. So let's try to virtualize something. The virtualization features are also configured by this table, and by a table similar to the segmentation table, and it looks basically the same, but it controls just which segment is loaded upon context change. And each row represents one virtual machine or one context, and the first one is reserved for the hypervisor. And it looks like this. Those numbers there, CS labeled with CS, DS, and so on, are the numbers of the entries in the segmentation table. So if the hypervisor mode is loaded, the hypervisor context is loaded, then all those registers, CS, DS, ES, and so on, are loaded with these values in this table. And so you're essentially completely reconfiguring the memory layout for each VM. There is this IP field. This is the instruction pointer. It's where, when the context is saved, the current instruction pointer where the next execution is instructed in executed in the VM is stored there, so that when the context is restored, the CPU can continue executing code from there. Then there is a flex field, which, what does it even do? It doesn't do, okay. The flex field is for the flex register. It's not accessible with any instruction except those branching instructions, because if you do a compare, and you compare two numbers, several flags are set, which indicate if one of those compared numbers are lower than the other, and so on, so that you can do conditional branches. And I need to save that, because if you do the compare, and afterwards you would branch, but then the context is saved, and another context is loaded and executed, the flags register most likely will have different values after the restore of the first context, which executed the compare, and then it will branch into the wrong direction. So I need to save this flags register also. And the last field, the privilege level, is still unused. If we actually want to enter a VM, or if you have a guest that we want to virtualize, we can execute a VM resume instruction. This is this explicit instruction which jumps into a virtual machine, as I told earlier. It saves, the CPU saves then the whole hypervisor state and restores the selected VM state. So if I want to return to VM1, for example, I would execute VM resume 1. And then the second row is completely loaded and it's executed. If I want to jump into VM2, then I would execute VM resume 2, and the third row is loaded. VM resume 0 is illegal. I never tried what it does, but I think it does nothing good. So it's undefined behavior, because that's a hypervisor state. You don't return into virtualized hypervisor state. Yeah, then the guest code runs. It does things. And if an interrupt, an exception, or exception like undefined opcode, when there is an instruction executed which doesn't really exist, then there is an exception raised by the hardware. Or if a privileged event occurs, the switch back to the hypervisor state occurs, and so the VM state is persisted, the hypervisor state is loaded, and it executes again after the VM resume instruction. And the stack now magically contains of the hypervisor context magically contains information what really happened. If there was a print instruction, then the stack says this VM wanted to print something. If there was an unknown opcode exception, it says the guest tried to execute an unknown opcode, and so on. Then the event can be handled by the hypervisor, and then after that you can return back into the guest you came from, again with a VM resume instruction, or you can choose another guest to return to. And that's not the whole hypervisor, but this is the core of the complete hypervisor. This is this VM entry, this VM resume loop, and the handling dispatching. What it does is, before it jumps into a VM, it enables interrupts, so that the timer basically can fire an interrupt and tell the CPU, I expired, do something for me. Then the VM resume is executed, the curly braces, no, the parentheses are for accessing memory. So this is a global variable, basically, where a 1 or a 2 is stored, so to enter VM1 or VM2. Then the VM code runs after executing the VM resume. Then if something privileged happens inside of this context, the next instruction will be executed again in hypervisor state. This is the clear interrupt bit, which disables all interrupts, because we don't want to handle interrupts while handling a trap or a hypervisor trap, a hypervisor event. And now the stack contains the virtual machine it comes from and the reason why it dropped back into hypervisor mode. And I put that from the stack back into registers R10 and R0, and after that I'm calling into function table based with an index in R0. So this function table, after handling this via the function table, I jump back into the loop, and then the cycle repeats, and the VM or another VM is executed again. This is how the jump table looks like. These are all events the hypervisor can be notified with. It's handle a segmentation violation if the VM doesn't adhere to the rules the hypervisor told it to do. Then if an invalid instruction is executed, if the VM tried to divide by 0, if there was a software interrupt raised, and so on and so on. Also, there is this, where is it? HV handle hardware access, the third from the bottom. This is the only handler I really implemented, and it looks like this. This is executed if the VM tries to print something, so it does a hardware access. And it's just another function. If a hardware access happens, then the stack contains the character to be printed, then the trap reason, the HV handle hardware access magic constant, and then the VM it came from. So because we already popped the first two values back into registers, we can now use the third argument, the third value on the stack as an argument, basically. So this get arguments call just puts the character to be printed into R1, and then I print R1, and then the function is completely handled, and I can return. So it should print the character. I also have a demo for that, and also going to show a bit more code because I think there is some time left. Yeah, maybe. No, that's wrong. So again, simulate. There are quite a few samples. There is a timer interrupt where I configure the timer, and the timer ticks in a regular interval. There is a function call test, add print. There is this basic hypervisor test, which I'm going to execute now. And there is a scheduling between two VMs, so that one VM is executed, then the timer interrupt fires, the second interrupt is, the second VM is executed, and so on and so on. What this code does is it starts a VM. The VM says, I am a VM, and after that, the VM just executes a halt instruction. The hypervisor gets notified of that, and it terminates itself too, because it has nothing more to do. And this looks like this now. Where is it? There. It's just basically one file. Here I set up the whole segmentation register. So I'm loading the segmentation. After that, I'm again with this instruction. After that, I'm going to load the stack, set up the virtual machine table, and tell the CPU to load that with this move control register VM table. Execute the VM resume, and this is the loop you saw on the this here is the loop you saw on the slides. Yeah, and here is just the complete handling code, which just executes a print string and then halts the hypervisor because I didn't implement that. Yeah. And here is the actual VM in this file. There are some interrupt handlers. And this is the whole VM code, VM startup, and the print string function where it actually prints a string. So another demo, I have this two VMs demo. And what's going to happen is that two VMs are going to be started, and they both print I am a VM, or VM1 started and VM2 started, And what you will see is that these letters are completely intermixed because the scheduling already happens, and there is about time for four or five character prints between each tick. And so you see 4 or 5 characters from the first VM, 4 or 5 characters from the second VM, from the first again, and so on. And after that, both of them are going to print. One is going to print A, and the letter A, and the other one is going to print the letter B. So we should see A, B, A, B, A, B, 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 and so on. Yeah, it works. The code is a bit more complex because it sets up the timer and so on. I'm not going to show that here because the time is almost over. I also have a debugger. The debugger is a bit like GDB, but not that powerful. If you start it with the memory image as an argument, you can just do the normal stuff like setting a breakpoint, disassembling code, printing registers, and so on. Oh, I forgot to explain why the registers are actually in memory. It makes the context switch much more easy, because if I have them in memory, I can reload the complete register set by just switching the register segment. If I switch the register segment to memory with a different base address, then all the registers are basically reloaded with different values. So for a context switch between the VMs, I don't need to use different moves or pushes to the stack for all the registers, where I can just switch the memory segment where the registers are aliased to, and I have a different set of registers. Yeah. The conclusion, the demo already was. Yeah, the simulator, as you see, it kind of works, but it's not as cool as I hoped it would be, because there are some things missing. The privilege levels are completely missing, and that's also the hardware virtualization is, to be honest, not really a hardware virtualization. It's more like a powerful hardware task switching mechanism right now, because there is no real privilege level. There is always one privilege level, and the hypervisor would need another higher privilege level than the kernel, for example, and there also need to be user mode, especially if you want to implement a para-virtualization or something like that. You may want to have a user mode where no privileged access is, like moving into the control registers or from the control registers and so on, is allowed. I made some very, very dumb decisions when designing this instruction set architecture, because it was the first in my life, to be honest. All the addresses I'm using are absolute. So you can't just copy segments of memory into a different location and just change the base address in the segmentation table. All has to be at fixed address. All the code, all the data has to be at fixed addresses defined at link time or assembly time. No, link time. Then I have this get arguments construct, because normally you would use a move. Yeah, go demonstrate. So the accessing stuff in the stack frame is not possible because every move is only allowed into the data segment, and I would try to access when pulling arguments from the stack in a function. I would use that on a stack segment. So that was something I discovered when implementing real code running on the CPU, and I fixed that by introducing the get argument construct. But you could just say, okay, accessing the stack segment with register 30, so the stack pointer, and register 29 for the base pointer is allowed on data and code segments, for example. And the worst decision I made is this whole thing implements an orthogonal CISC instruction set. That means it has variable length opcodes. It has the possibility to access memory on every instruction you can imagine. Every instruction that is implemented in the CPU is able to access memory. So on every instruction, I needed to implement a check if the segmentation rules are violated or not, and that was kind of a pain. But it makes the whole reason for that is it makes the instruction set very easy to understand for beginners. And this simulator is supposed to be for students and beginners. So maybe that was not the worst decision, but it made the implementation very, very hard and painful. Yeah, nevertheless, if you want to play with it, there is a GitHub page. It's not yet online, but as soon as I click on public, then it's online. Yeah, so if you have questions about it, I'm going to be here today and later in the launch, perhaps on tomorrow. If you want to extend it, please do so. Yeah, that's basically it. Thanks first. Are there any questions? No questions? Okay. Well then. Building actual hardware. So the question was when I'm starting to build actual hardware, the CPU, implementing the CPU in hardware. It's not designed to be built in hardware. It is possible, but implementing CISC instruction set computers is very, very hard, or is harder than RISC. And this whole construct with this segmentation and the hardware virtualization would need some kind of microcode, and it is perfectly possible to build that, but it's going to be horribly slow, because I'm going to need several clock cycles for every micro instruction, one clock cycle, for example, for every micro instruction, which then resembles a complete normal instruction you would write with an assembler. So, for example, like if I need 10 instructions to perform an add with all this memory access and so on, and I have 50 megahertz clock, then the real execution speed of the CPU would be like 5 megahertz or something. Perhaps I'm going to do that in a weekend or something and put a half-finished project on GitHub, but I didn't start yet. So, nobody? Nobody else? Okay, if there are any questions, as I said, I'm going to be in the launch or running around in this building. Yeah, thanks.